Okay, so our goal for this video is to perform forward elimination on this matrix A, which is 1, 3, 2, 6, 2, 4, 2, 10, 6. And then we'll do it with partial pivoting, basically meaning that anytime I need to pivot, I will. And to remind you, what that means is for partial pivoting, we want maximum value in a column to be along the diagonal. So again, if we look at our diagonal, which are, I'll highlight them, are these three. We're going to do this one column at a time, but in this first column, we see that 1 is not the maximum value. The 6 is. So we're going to pivot this row with this top row immediately before we begin our forward elimination step of Gaussian elimination. And we'll keep track of our pivots because at the end of the day, we'll see if there's an odd number of pivots or an even number of pivots because the determinant of this matrix is some value. I'm going to say the determinant of A, is something. We don't know what that number is. And depending if we do an odd number of determinants or an even, the determinant of the final matrix will end up being either positive or negative or whatever this number is. Maybe I'll just see what that number is real quick. Determinant of A. If I do it in MATLAB. It's very small, which makes me think that I made a bad equation, but that's besides the point. Let's go ahead and see how we do our forward elimination here. So first thing we want to do is pivot. So we'll pivot we'll say, I'll call it A1. This will be A0. That's our initial. And what we'll do is we will go ahead and actually, let me move my space out of the way. We'll go ahead and pivot, have the 6 in the top row, 6, 2, 4, and we'll switch that with this row. We do not need the column in order of descending. We don't care about that. What we do care about is that now the maximum element in that column is along the diagonal. That's a 6. So our first step will be to eliminate the 1. Now that we have made this the max. So what we'll do is find our modifier. Our modifier, which will be ultimately L21, if we were to do an L matrix, will be 1/6. Because what we want to do is multiply this top equation, the one we're modifying, by some value that'll make the 6 equal to a 1. Well, 6 times a sixth is equal to 1, and that's why we'll choose that. So we'll say that our E1 modified will therefore be 1/6 times 6 to 4. That's our top row. And that will become 1. 2/6 when we multiply across is going to be a third. I'll just write that as 0.333. 4 times a 6 is 2/3, which will be 0.667 if we're chopping or rounding. We're rounding in this case, but if we were to consider number significant digits, that's what we would do. So our new row 2 will be our original row 2 minus our first equation that's been modified. This would be 1, 3, 2 minus 1, 0.333 and 0.667. And if we do that, we subtract corresponding elements. So 1 minus 1 is 0. 3 minus 0.333, 3 minus a third will be 2 2/3, which will be 2.667. And then we'll do 2 minus 2/3, which would be 1 1/3, 1.333, like that. And of course, I'm going to double check with my calculator, make sure I didn't screw that up. Yep, we're good. So this is our E2 new. We will substitute that back into here. I'll still call this our A1. Granted, it's different, but we haven't pivoted. We've only pivoted once. That's 6, 2, 4. We're going to replace this now here. So 0, 2.667, 1.333. And our last row is exactly the same. Cool. So now what we want to do is try to eliminate the 2. That's our next step, eliminate the 2. So again, our multiplier will be L31 because that's in the third row, first column. If we were to make an L matrix, that's going to be some number multiplied by 6 to make it match 2. Well, that is 2 over 6, which is, 1/3. So we'll say that we'll modify that top equation again, E1 mod. That will be 1/3 times 6, 2, and 4. 6 over 3 is 2. That's what we want because we want this number to match that number. 2 over 3 is 0.667. That's 2/3. And 4 over 3 is 1 and 1/3. So now what we'll do is E3 minus E1 mod, which will be our 2, 10, 6. That's our original E3, minus our modified equation 1, which is what we just found. And now we subtract. 2 minus 2 is 0. If we do 10 minus 0.667, we will get 9 1/3, which we'll write as 9.333. 6 minus 1/3 will be 4.667. Let's double check that in our calculator. Yep, 4.667. And that will be our new matrix. So this is going to be 6, 2, 4, 0, 2.667, 1.333, 0, 9.333, 4.667. So that is our new matrix. I'm going to use a different piece of paper now to continue this. That's fine. So now what we see is we want to eliminate this element, but what we want to be sure of is that we have the maximum element really between these two, because this top row we're done with. We're just focusing on these two. Between these two, the maximum should be along the diagonal. So we are going to pivot these 2 rows this time in order to have our maximum value between those two in the middle. So I'll say that A2, I'll say 2 because we've done 2 pivots, is 6, 2, 4, 0, 9.333, 4.667. Again, because we're switching those two. 0, 2.667, 1.333. So we have pivoted. This is our second time pivoting, and we've noted that for our problem. Now what we're going to do is eliminate 2.667. So we need to multiply the second equation now, because we're always going to use in that column to eliminate, we're always going to use the diagonal. So if I had a 6 by 6, it would always be the element along the diagonal. It wouldn't be the top one, because what happens is if you modify the top one, you would do E3 minus E1 modified. You'd have 0 minus some value, and this becomes non-zero, and that's a problem. We want these to stay 0. So if this is changing because we're subtracting something that's non-zero, that's a problem. So that's why we reference this to this, because this first element is 0 already. 0 minus 0, no matter what the multiplier is always going to be 0. So that doesn't cause us to backtrack, essentially. So to eliminate 2.667, we need to make that 9.33 match that. So we'll say that L32. Let me make sure that you can actually see that. L32 will be the multiplier that would go here in the L matrix. That has to be 2.667 divided by 9.333. And if we do that in our calculator, just to have an actual number, 667 divided by 9.333, you get some ugly thing, which is, approximately 0.2858. So what we'll do now is modify the second equation. E2 mod will be this 0.2858 multiplied by 0, 9.333, 4.667. Sorry, my paper keeps turning. So that first term is going to be 0. This second term, if you actually multiply these out, they wouldn't be exactly 2.667 because of the rounding. But because we know we're eliminating this, this will end up matching this value no matter what. We have to have that match in order to do Gaussian elimination. We could check. I'll multiply it out just to see 0.2588 times 9.333. That's 2.667 with rounding or chopping. So it actually is fine. But there are some cases where this number may not match exactly. But it's okay for this element because we know we're eliminating it. So we will always make sure that this ends up matching the thing we're trying to eliminate. And now we'll do our last thing, which is 4.667 times 0.2858, which is 1.334 because of the rounding. 1.334. If we were to do this exactly, it would probably be exactly a third. But we're going to keep it with the sig figs for now. Then what we'll do is E3 minus E2 mod. E3 is 0. 2.667, 1.333 minus 0, 2.667, 1.334. Again, do the rounding. So E3 was this guy. E2 mod is that guy. So we get 0, 0, 1/3 minus 1.334 is 0, negative 0.001. And that's what we will plug into our matrix here. Oh, is that right? Let me double check. Yeah, that's right. 1.333 minus 1.334 just to be double. Yeah, I don't know why I was going crazy. Okay, so I'll plug that in now. We'll say that A2 that stays the same. Second row is the same. 0, 0, negative 0.001. So because of our sig figs, we end up with this value here being non-zero. But if I plug it into MATLAB, this ends up being exactly 0. And that was just by chance. It's not like I planned for this. But what do we know if this is 0? Well, the determinant of A2 will be the product of the diagonals because we're in this forward elimination form. So that would be 6, 9.333 times negative 0.001. But again, if we were to do this exactly, just out of reference, this would be a 0. I'll say if exact, which has our determinant of A2 is 0, which means our determinant of A initial, that equals negative 1 to the power of P, how many pivots we did, times the determinant of A2. Well, since this is 0, this doesn't matter, but we'll be thorough. We've done 2 pivots. Negative 1 squared is positive 1. So the determinant of A naught ends up equaling the determinant of A2 in this case, which equals 0. Because the determinant of A2 with this exact value would be 0. If it wasn't exact and we were to keep it like this, it'd be 6.9.333 times negative 0.0001. It's 0.055998. Because we did 2 pivots, the determinant of our original matrix with the sig figs would be exactly that. If we were to do forward elimination on that original matrix. So if we did forward elimination on this without pivoting, the determinant of this, remember I said it's the determinant of some number, that number, if we do sig figs, would be that 0.05598 or whatever it was with rounding, and ends up being 0 exactly. So because we pivoted twice, the determinant of our final matrix we had is equal to this. If we stopped here with pivoting and didn't pivot these, that would mean we did 1 pivot to get to the forward elimination form. If we didn't switch these, we left it as is and did our forward elimination with the elements in these elements in these spots as is, that would be 1 pivot. Then our determinant calculated would end up being negative 0.05598. And then it would still be 0 if it was exactly. But if we kept rounding, it'd be negative. And we just have to note, we did one pivot. The determinant of that final matrix is not equal to the determinant of this. It's actually equal to the negative of it. Okay. I hope that this helps with partial pivoting. The main thing is that you want your diagonal elements when you're doing these steps to be the biggest in that column, depending on, I guess another way of thinking about it, if you look at the column, maybe I'll just do one more quick thing. Let's say I give you some giant thing. 0, 2, 6, 3, -27, -24, 1, 4, 0, 0. I'm just making up stuff. -3 and 5, whatever. Ignoring the forward elimination stuff, I just want to show, if we were to pivot based on this first column, we would want the 4 to be at the top because it's the biggest. And remember, these are our diagonals here. This is the diagonal, this is the diagonal, this is the diagonal, that's a diagonal. And we will pivot this top row up. Let's pretend we didn't do that, though. I just want to show an example of what we would do here. We're just going to look at the elements that are below our diagonal, because the ones above don't really affect our Gaussian elimination. So that means we'd want the 6 to be moved to the 2. We would want the 4 to be moved to the 1. Of course, this would change dramatically after we start pivoting things and eliminating, but just to show you, we're always going to make sure that in that column, that the maximum element that is in the rows below the diagonal has to go in the diagonal spot. So max element in column has max element in column below diagonal, and including the diagonal, of course, below diagonal and including, has to go to the diagonal. Think about this. If you have questions, let me know. I hope this didn't confuse you more, this extra bit, but I hope that this example made things clearer with regards to pivoting, because I made sure to design the problem to have to pivot twice. Okay, if you have questions, reach out. Thanks.